Okay, so the next type of antiderivatives we're going to talk about is the more complicated trig integrals. So we just spent one day in the partial fractions. Make sure that you get your questions answered. Oh, that reminds me. On WebWork, some of you are emailing me questions on WebWork. That's perfectly fine. But I just ask that you use the email instructor button at the bottom of the page on the problem that you have the question about. Don't do a screenshot or tell me, a number set, a straightforward email. Just on the page where you're having the question, at the bottom of the page, there's a button. It says email instructor. So click on that, and then there'll be a chance for you to write me a note and be specific about where your question is. And that helps me tremendously because I get a direct link to your problem super fast, and then I can help you. So just use that email instructor button when you have WebWork questions. Okay, so the partial fractions, make sure you get your questions answered. Office hours, if there was still had difficulty with that. So we're going to move on to more complicated trig integrals. So here's the strategy. First step is to simplify or change the form of the given rate function using one of two things. Either going to use trig identities to change this thing around or reform it, or just algebra and arithmetic. So usually these more complicated trig integrals start by you doing some just rearranging or algebra or applying trig identities. That's a real common one. You're applying trig identities, so now you're looking at something that looks different, but it's still equal to what you had before. Make sense? And then what's the goal? In order to set up for, you're doing that in order to set up for one of two things. Okay? Either just a simple or straightforward trig antiderivative, or very commonly, you're doing this step one in order to set up for undoing the chain rule. Undoing the chain rule. So we're making it look different in order to get something easy or to do undoing the chain rule. That's the basic premise of these. So you see how undoing the chain rule just keeps coming back. It becomes part of every other technique that we use too, right? We saw it becomes part of lots of the undoing the product rule problems. Sometimes it comes at the end of a partial fractions problem, and then oftentimes it's in these trig integrals. That's why undoing the chain rule is so important. And you always are asking, that's the one you're always on the lookout for first. Or trying to, in this case, trig integrals, you're trying to reshape the given function to set it up for undoing the chain rule. Okay, so here is the identities. And this in the homework post for Friday's homework, I gave you a link to a doc that has exactly this. Don't have to write it down. You can print it out. Okay. These are the most important identities that come in terms of solving these more complicated trig integrals. So the basic definitions of tan, cosecant, cotangent, and secant. The half angle formula is crucial, really important. Pythagorean identity comes in a lot. And then the variations on the Pythagorean, and then the double angle. Okay. So in terms of, do you have to memorize these? So what I do is on exam one, I kind of split the difference with you. On the front cover of the exam, I have this exact sheet, but then everything's blank. Like all the left sides of equal signs are all blank. So before you start the exam, you can fill it out for a bonus point. All right, so yes, you memorize it, but you get a bonus point for filling that out. And then as you work the exam, you'll have them all. Okay? So that's how we'll handle that. So it won't even take you 10 or 15 minutes to memorize these so that you could fill it in yourself. It'll be easy. All right, so let's do some examples. Okay, so there's our identities. No, don't want to do that. Okay, You can still read those, right? Okay, first one we want to do is cosine squared, tangent squared. Okay, so again, using identities or algebra to reform this or get something that's going to make our life easier. So what might we do with cosine squared, tangent squared? Yes? Okay, good. So he recognized, so we have some different choices here. Here are the choices we have. Look, cosine squared, we could use the Pythagorean identity and say it's 1 minus sine squared. Doesn't look like it makes it any easier. Cosine squared is also equal to 1/2 1 plus cosine 2x. Now that's really bad because you don't want to have different arguments in the same integral. So here, then you'd have cosine 2x and tangent squared x in the same integral. That's always, you want to avoid that. That will make it unsolvable. In all your functions, you want to have the same arguments. Same argument, meaning what you're plugging in. So that's not good. So then what he saw was, oh, tangent is sine over cosine, so tangent squared would be sine squared over cosine squared. And you should immediately see that that is very helpful. Why? Because then you have a cosine squared in the numerator and a cosine squared in the denominator, and those go away. Leaving okay, which comes to a very essential fact about solving trig identities. Whenever you get sine squared or cosine squared, or there could be a different argument here, sine squared of 3x or sine squared of 10x or cosine squared of 15x, whatever, it's always, what can we do to do this now? You want to see it? Half angle formula. So there's just a basic fact that you have to remember and be on the lookout for. If you ever have just plain old sine squared or cosine squared, it's the half angle formula. It shows up all the time. So we're going to write that out. 1/2, 1 minus cosine 2x, and then it's easy. We just have two different ones to solve, right? So 1/2, and antiderivative of 1/2 is? Antiderivative? 1/2 x. And then we have 1/2, negative 1/2 cosine 2x. Antiderivative will be? So it'll be negative sine 2x with something out in front. So we have to figure out what factor we have. So because it's 2x, we think about taking the derivative. That's going to mean we need what? A 1/2. But then we already have another 1/2. So we're going to need 1/4. 1/4. So I skipped a step there. I actually distributed in my head and then did each one separately. Plus c. Plus c. Okay, so essential fact. You just have to memorize it and be on the lookout for it. Whenever you get integral of sine squared or sine squared of something like 2x, 3x, 10x, 100x, or cosine squared of something x, half angle formula, and you're pretty much done. So that's a fact you have to remember and be on the lookout for. Yeah. Well, so what? No, you can't. Chain rule doesn't work. How can you? What would you need for chain rule? You'd also need what? Another sine squared x times cosine x, right? You'd need a times cosine x for it to be undoing the chain rule. Yeah, so there is no chain rule that leaves you with sine squared x. Okay, questions on this first one? Okay, how about sine cubes? How about this one? Is it undoing the chain rule? What else would we need? We need a cosine. If it was sine cubed x times cosine x, undoing the chain rule. Home free, you're done. But it's not. It's just sine cubed x. So we got to come up with something here. Someone said split it up. What do you mean by split it up? Okay, yeah. So we could do sine x. First of all, split it up into sine x times sine squared x, because we got lots of options for sine squared, right? Or at least a couple. So with sine squared, we have options. We can do things. Do we want to use the half angle identity here for the sine squared? The problem with that, again, is then we'd have an argument x and an argument 2x. And that's like, those never work. You can't do the antiderivative like that. You got to have the same argument. So we'd have an x, and if we put in the half angle, then we'd have cosine 2x. Different arguments. Stay away from that. All right, so what else could we do? What else is equal to sine squared x? Okay, we could do 1 minus cosine squared. We could use the Pythagorean. Did that help? So either you can see it, or you could, if you're not sure if it helped, what other step could you do here? We could distribute, right? We could distribute and see if we can do each one separately. Can we do sine x? Easy, right? Can we do sine x times cosine squared? So antiderivative of sine x is negative cosine. And can we do this one? It was on your quiz, right? This is quiz. How do you do it? Undoing chain rule, right? You've got essentially the derivative sine x of the interior function. So it's undoing chain rule. Attempt is 1/3 cosine x cubed. Now, is it minus or plus? So when we do this as a derivative, we will get what? Times negative sine. And then that would make that plus, but there's a minus there, so we need plus here. So the minus sign that we get in the derivative becomes that minus sign. Plus c. So see what happened. We did some algebra, we pulled it apart, we used an identity, and that identity, chosen correctly, set this up for easy and undoing the chain rule. That's the gist of these. That's the feel of these more complicated trig antiderivatives. So let's try a couple more. Any questions on that one? So there's some trial. So if you're not experienced with this, then there's going to be some trial and error. Some trial and error involved. One thing you know is a dead end. Again, if you get arguments on different trig functions that are different, like you have a cosine 3x and then you have a tangent x. Whenever you come to something like that, that's a dead end. It's a dead end. You got to go back and try something else. Okay, next one. Sine 2x, cosine x. That's the easy one you should be able to do. Real easy. And then harder. Okay, so that we have time for this longer one. You should have found the answer was negative 2/3 cosine cubed x, or cosine x cubed. Did you get it? Sine 2x is 2 sine x cosine x, which ends up, so then we have 2 sine x cosine squared, and that's the third time we've seen that problem today, basically, with a 2 now. Right? So sine 2x, 2 sine x cosine x, then you'll have a cosine x times cosine x is cosine squared. We've got that same problem again, sine x cosine squared. And then that's just that, cosine cubed, undoing the chain rule. So if you didn't follow that, then just write that answer down and then work through that later. But it's basically, after you apply that identity, it's the same problem we've seen twice already today. So this last one, secant to the 4th, tangent to the 7th. So what we're looking at here is so we want to think about, it's pretty complicated. So we want to think about setting up, undoing the chain rule. Setting up, undoing the chain rule. So to set up, remember in the chain rule, we have something like this. If we're going to undo the chain rule, we're thinking about something like that. So we need to be on the lookout. So if this is a trig function, then this is a trig derivative, right? So for instance, in this case, we can consider maybe an interior function of tangent. That would mean the derivative of what? Secant squared. Or maybe an interior function of secant that would result in a derivative of secant tangent. So if we're undoing the chain rule, what we're trying to do, we're trying to isolate a derivative of one of the trig functions. So let's start with this first one. So maybe secant squared. So can we isolate a secant squared here? And then what would we need? We need everything else to be some power of tangent, and we'd have it, right? You see that? If everything else was some power of tangent over here, and then we had secant squared, then we would have it. So if we pull out secant squared, what's left? Secant squared, x, tangent to the 7th, x. So again, if I can, in those brackets, if I can get everything some expression of just tangents, then it'd be home free because I've got the derivative of tangent right here, secant squared, for undoing the chain rule. You following? So can I do that? Can I write all this as tangents? How can I do that? How can I write secant squared as in terms of tangent? Right here, secant squared is tangent squared x plus 1. And then this is tangent to the 7th. So now we're going to distribute inside the big brackets there. Holding on to my secant squared. If I distribute, I'll get tangent to the 7th. And plus tangent to the 9th. And do you see that we're home free now? Do you see this? If I now combine the secant squared with each of these, I've got undoing the chain rule on both of them. What would this be? So secant squared times tangent to the 7th x, antiderivative would be? Anyone see it? 1/8 tangent to the 8th. And then distributed the secant squared to tangent to the 9th. I would have 1/10 tangent to the 10th. So, can you pull out a derivative of a basic trig function? In this case, maybe secant squared or a secant tangent, and then get the whole rest of the thing as powers of this? We could, right? So we could pull out a secant squared and rewrite the whole thing in terms of tangent, and that sets up for undoing the chain rule. Plus C. Okay, here's